Hello everyone, welcome to our presentation. I am Yao Sun. Here I present CGNet, Conditional GIS-aware network for individual building segmentation in VHR SAR images. Buildings are the dominant structures in urban regions. Building analysis from VHR SAR data are of great importance for urban SAR applications, yet highly challenging owing to the complexity of SAR data. Researchers have developed tailored algorithms to analysis individual buildings. However, these methods are difficult to be applied in large areas. More recently, buildings are segmented in large scale using deep networks, however individual buildings are not recognized. As shown in the figures, in semantic segmentation, all buildings are assigned the same label, while in individual building segmentation, each building is identified as one class. The task of individual building segmentation from SAR image is highly challenging. As we can see from the figure, consecutive buildings in the physical world may be difficult to be separated from each other in SAR images, and separated buildings in the real world might overlap with each other in SAR images. In this work, intended to segment individual buildings in a large urban area, we propose a workflow exploiting SAR images and building footprints. We propose a CGNet that imposes constraints on the learning process to improve the network performance. Now we present the network architecture. Since footprints from GIS data provide precise geometry and location information, we resort to exploiting such cues in our task and devise a network module that performs a conditional GIS-aware normalization. In a naive conditional normalization procedure, as in equation 1, XB denotes feature maps extracted from the B convolutional block, gamma B and beta B represent a scale factor and a bias. In our case, we want to normalize feature representations learned from SAR images, conditioned on GIS data. We reformulate the equation to equation 2. MGIS is the mask of the building footprint. Gamma and beta now are learned for the pixel at PQ in the channel C of XB. Such a design enjoys an advantage that normalization parameters are learned in a data-driven manner, and thus these parameters are expected to be more adapted to XB. Our network, termed as CGNet, utilizes the CG module. We employ VGG16 as the backbone of CGNet. Outputs of the last three convolutional blocks are upsampled and fed into the CG module. Meanwhile, footprints are imported into the CG module as complementary inputs in order to yield final predictions. The proposed method is tested in Berlin area using a Spotlight Terra SAR X image and building footprints from GIS data. A highly accurate DEM is used to generate ground truth annotations. To evaluate the performance of networks, we calculate the F1 score, where P and R denote precision and recall, respectively. In addition, the IOU and overall accuracy are also calculated. In our experiments, we compare four models, FCN, FCN-CG, DeepLab v3, and DeepLab v3-CG. FCN and DeepLab v3 are regarded as baselines. Both FCN-CG and DeepLab v3-CG are our proposed networks with different backbones. Numerical results of different models on our dataset are listed in the table. It can be seen that all metrics are improved with CG module. DeepLab v3-CG achieves the best performance in all four metrics in our dataset. The improvements achieved by FCN-CG and DeepLab v3-CG demonstrate the effectiveness of the proposed CG module. All models achieve relatively high OA. This is because OA is computed by considering all pixels, while non-building pixels account for a large proportion. For qualitative evaluation, we visualize several segmentation results. Pixel-based true positives, and false negatives are presented in green, red, and blue respectively. It can be seen that for buildings with simple structures such as the building in column A, all models are able to offer satisfactory segmentation results. For buildings' complicated shapes, a general improvement is observed from FCN, DeepLab v3 to FCN-CG, DeepLab v3-CG. Here we show the segmentation results in the study area obtained by DeepLab v3-CG. The building segments are plotted with different colors. RG and AS denote the range direction and azimuth direction. To conclude, in this work, we address the issue of individual building segmentation from a single VHR SAR image in large-scale urban areas. We propose a novel conditional GIS-aware network and introduce building footprints as complementary information. Experimental results show that the proposed CGNet effectively brings improvements with variant backbones. In the future, we are interested in applying the proposed workflow to areas of various urban morphologies and to Terra SAR X and Tandem X strip map images. Thank you for listening.